In this video, we're going to look at how to use phototransistors in simple circuits. You should be familiar with the use of voltage dividers, and you should also be familiar with using LEDs and transistors in simple circuits. LEDs are fairly simple devices. If we apply a potential difference across an LED, an electrical current will pass through it, which in turn will cause the LED to emit light. The question is, can we reverse this? And the answer is yes. If we instead shine light onto an LED, a current will pass through the LED, though now in the opposite direction as before. If we place a voltmeter across the LED, we'll find that we can measure a potential difference across it. What this means is that we can use an LED to detect light. Here I have a red LED connected to a multimeter set to measure the voltage across it. I have pretty bright light set up for this recording, which is generating about 0.1 of a volt. If I put a bright LED over top of it, we see that a considerable voltage is produced. Note that the voltage produced will vary depending on the light source and the LED used. If I now measure the current passing through the LED, I see that only a tiny current is passing through it. In this example, only about half a microamp. Clearly, if we're going to use an LED to detect light in a circuit, we'll need to amplify the tiny current which is created. We can do this by attaching the LED to the base of a transistor, as shown here. If a voltage is applied to the circuit and the LED is not illuminated, no current will flow through the transistor. When the LED is illuminated, a small current will pass through the base of the transistor. This will cause the transistor to become conductive, and a much larger current will pass from the collector to the emitter. Note the orientation of the LED in this diagram. The LED here is said to be reverse biased. If the LED was flipped, then the LED would instead emit light and the transistor would always be switched on. Now this circuit that we've built is equivalent to a single component. On the left we've used a photodiode and a transistor, which we can replace with a single phototransistor. The phototransistor that we'll be using in this video is one which is sensitive to infrared light. It's encased in an opaque black plastic which visible light cannot penetrate, but which infrared light can easily pass through. Though infrared light is not visible to human eyes, many cameras, including the one that I'm currently using, will be able to detect near infrared light. Here, infrared light is being displayed as a light violet color. If infrared light passes through the phototransistor, we can see its internal structure. Again, if you'd like to do this experiment at home, you'll need to use a camera which can detect near infrared light. Now let's see how to make use of these. Our goal is to set up the phototransistor in such a way that it will output a high or low signal depending on whether it's illuminated or not. We can do this with the following circuit. Essentially, a voltage, labeled here as VCC, is applied across a resistor in series with a phototransistor. This setup should make you think of a voltage divider, though strictly speaking this isn't one, as the phototransistor doesn't have a fixed resistance value for a given intensity of light. Nonetheless, for our purposes, we can pretend that the phototransistor is a resistor of a few hundred ohms when illuminated and several mega ohms when in the dark. It's safe to make this simplification due to the extreme differences in these values. If our voltage divider is to have distinct outputs, a resistor in the order of 10 kiloohms will do just fine. We can see why if we use the voltage divider equation. For the light case, we calculate an output voltage of 0.01 VCC, which is clearly a low state. Calculating for the dark case, we find an output of 0.99 VCC, a clear high signal. Sometimes it will be useful to have the outputs flipped, which can be done simply by switching the order of the resistor and phototransistor. Here the output is high when light is detected and low when there is no light. Let's see how this works. Here I have a phototransistor pointing at an infrared LED which has its collector connected to about 5.1 volts. I've set up the multimeter to read the output voltage of the voltage divider. When there's nothing blocking the phototransistor, we get a high output of roughly 5 volts. And when we block the infrared light, we get a low of about 0.1 volts. If you'd like to take this further, the next step is to interface the output from the voltage divider with a GPIO pin and write a program to read when the GPIO pin is high or low. In another video, I'll show you how to use an infrared phototransistor to make a photogate, which can be